Hello and welcome to Intermediate Algebra, Unit 4, Lesson 2, Solving Systems of Equations Using the Method of Substitution. Our lesson objective is exactly that. We're going to learn how to use the method of substitution to find the solution to a two-variable linear system of equations. And by the word substitution, we just mean replacing one variable with something that it's equal to. So in the first lesson of this unit, we learned what it was meant for a point to represent the solution to a system, and then we found the solution by graphing two equations and locating the intersection. As you even saw in that video, this isn't always really precise or really practical. If the numbers were really big, you'd have to have a really big graph, and telling which number exactly was the solution would be tricky. So if we can work directly with equations, solve these algebraically now, this will allow us more precise solutions for a larger breadth of problems. So this method works best when you can easily isolate one of the variables. You can put one of the equations in the form y equals and have an expression on the other side with x's in it, or put one of the equations in the form where x equals something with y's in it. The most obvious case is with both lines, and if we're working with lines, that's all we will work with here, though you can have systems that are not lines, but you won't see that till much later. When you have both lines are in slope-intercept form, substitution is actually very simple. So here's an example with both lines in slope-intercept form. And the thing to keep in mind is that when I say y equals 3x minus 4, that means anywhere I have a y, I can write 3x minus 4. So if I did that in the first equation, it'd be a little silly, but I'd get 3x minus 4 equals 3x minus 4, which would indeed be a true statement, because I was already told these were equal. So, and then I have y equals negative 2x plus 5. Now this is a system. They both have to be true at the same time. So if in this equation it's true that y is 3x minus 4, it's also going to be true in this equation. So I use that to turn my second equation into an equation of one variable. I replace the y here with the 3x minus 4 there. And you can see that right here. And then I solve this equation that is now in one variable. So if I have one variable in one equation, I can solve for the variable. When I have two variables in one equation, I can't, but if I have two variables in two equations, then I can. So this one variable, now I have x's on both sides, so I have to choose a side to put the x's on, and I happen to choose the left. So I want to zero this one out over here by adding its opposite. So I add 2x to both sides, gives me 5x minus 4 equals 5. Now if I put the x's on the left, I want to put the numbers on the right. So I add 4 to get rid of the subtracted 4 to zero that out on the left. And I get 5x equals 9 and x equals 9/5. Now notice this is not an integer. Not all of your solutions are going to be integers. As a matter of fact, in life, most solutions are not integers. But that would be harder to see on a graph. You wouldn't really know if it was 1 4/5 or 1 3/5 or exactly what it was, but using algebra, the 9/5 is very clear. So that would be an advantage using algebra. But now you might be saying, we only know what x is. Well, now we know what x is. We can, in either equation, put in x equals 9/5, and then we'll have an equation with just a y in it. We can find y. And if we do, we should be able to do that in both equations and get the same answer if this truly is correct. So let's see how that works next. So I have x equals 9/5, and I put that in place of x in one of my equations, and it doesn't matter which one. And I can check my work. If it works here and I want to be really sure, I can also check it in the other equation. So remember, when you're multiplying 3 times 9/5, when you multiply fractions, you multiply the numerators together and the denominators. And students have a really hard time when one of your fractions isn't a fraction, when it's an integer. Well, write it as an over 1 if that helps you, Or just simply, if you have 9/5 three times, you have 27/5. You multiply the integer times the top. And that'll increase. How many fifths more do you have? You have 3 times as many fifths, so you have 27/5. You can use your calculator to do this. If you really struggle with fractions, learn how to use your calculator to do it and see me for help, because if you don't, you're not going to have a good time, because we will see lots of fractions here. It'd be better if you could learn how to do them manually again without your calculator, but if you can't, please learn how to use the calculator to do fraction arithmetic and get fractions as answers from it. So, the end of that lecture. When I subtract 4 from something in fifths, I have to write that 4 as if it's fifths, and 20 divided by 5 is indeed 4. So then now I have a common denominator of 5, and I subtract the top. So when you add or subtract fractions, you have to have a common denominator. When you multiply or divide, you do not. Multiplication division is actually easier. So I get y is 7/5. And if I put these into the other equation, I will see that I also get a true statement. So here's our second example, and this one is not in slope-intercept form, so I can't just simply take the y of one, take 3x minus 4 and put it in for y in the other. First I have to do is isolate a variable. Now, the reason I know substitution will work well for this is because I do have a negative 1 times y, but this x has a 1 in front of it. If I have a variable with a coefficient of 1, I solve for that variable, and I won't end up dealing with fractions in my algebra as I try to find my values of my solution. So it's easy enough to isolate this x here, just by moving the minus 3y over to the other side by adding it to both sides. And that's what I'm going. Now you could instead isolate this y, but you're going to have to end up dividing by a -1 when you're done. But that actually doesn't give you fractions to work with, so that would be an option. But I also want to show you that you don't always have to isolate a y. You can isolate an x. That's done on the next slide here. So this second equation gets rearranged into this. This is now your second equation. And I will start numbering your equations very soon here. That's equation 1, that's equation 2. And it's important to remember which is which, because now I want to take, since I'm working with equation 2, I want to put it back into the other equation in place of x. If I just put it back into the one I started with, I get something equal to a self, and it doesn't give me any answers. So in the first equation, I'm going to take this x and replace it with -3 plus 3y. And I did that typed out here. You can see I put it in parentheses because I want to multiply the 2 times the entire value of x, so I have to put the value of x in parentheses. When I multiply 2 by -3, I get -6. 2 by 3, I get positive 6y. Now I group like terms. I have a 6y minus another y, so that leaves me 5 y's right here. And then I'm left with the -6 by itself. I add 6 to both sides, and I get 5y equals 10. Divide by 5, I get y equals 2. Now once again, I have y, but I also need x. I can put this value of 2, replace y with it. Here's the substitution. Substitute 2. We use substitution several times in this method for y in one of the equations in order to find the value of x. So I can go back to the equation I solved for x. It's better to go back to an original, but here I also showed you can use the isolated x equation. If you go back to an original, it'll show you if you made a mistake somewhere else along the way. But I took the value of y equals 2, and here was that equation 2 that I solved for x. Replace that with y. Now I know x is -3 plus 6, which is 3. And if I put in x is 3, y is 2 into my first equation, I should get 4. And I get 6 minus 2, and that is indeed equal to 4, so that seems to work there. If I put x is 3, y is 2 into the second equation, I should get -3. So I get 3 minus 6, and that indeed is -3. So yes, this is a true solution. X is 3, y is -2. We often write that as a point. I'm sorry, y is positive 2. X is 3, y is 2. we often write that as a point, and there's how you solve that one. Now this one again, this system we started with works well with substitution because we could easily isolate an x. So here's another one. Now I'm going to start numbering the equations here. Most of this one is typed out. So I number my equations at the bottom of this slide so we can keep track of what we're working with. So I decide to rearrange equation 1 to solve it for x. And then in equation 2, that was x. There's the x there. I just put that in for x there. And now I have an equation with just one variable, y. So I can solve for y. I can find a value for y. So the negative y here and the negative 3y here gives me this negative 4y. I add 1 to both sides to get this. And then when I divide, I get negative 4y equals negative 8. That should be a positive 2. That is a mistake. So y equals 2. And then x plus 2 has to equal negative 1. So x would have to equal negative 3. So the solution is y is positive 2, x is negative 3, and I did not check my work even though I had a signed number arithmetic mistake there. I would have found it if I went and checked both equations, and I wouldn't have found that my solution worked. This solution, where y is positive 2 and x is negative 3, should work. So the solution is negative 3, 2. So negative 3 plus 2 is at negative 1, yes. And in the second equation, negative 3 minus 3 times 2, does that give me negative 9? Yes, it does. So this is the correct solution. There's a mistake on your study guide too then. So be aware of that. And let's move on. See, that's why you check your work. I'm modeling bad math habits. I should not do that. I'm going to solve this system. Now, we saw this one in the graphing. But let's show what happens. How do you know? We ended up getting parallel lines and no solution. But how does that come out in algebra? Well, when I replace, so I have equation 1 and equation 2. So I'm taking the y value from equation 1, y is equal to 1/3 x minus 3, and putting it in for y, replacing it for y in equation 2. So after I do that, if I, and this time I add, I want to put all the x's on one side, so I decide I'm going to put them on the left, so I subtract 1/3 x from the right, I have to subtract 1/3 x from the left also. The problem is, on both sides, the x term becomes 0. So when that x term becomes 0, I'm left with negative 3 equals negative 4, which is what we would call nonsense. Negative 3 is never equal to negative 4, so there is no solution. Now, if I had gotten negative 3 equals negative 3, that's always true, so that would be the case where there's infinite solutions. But in this case, I get a false statement with two numbers, so it's not true. Let's move on to the next problem. So here is the one where we got infinite solutions, and let's see how the algebra works out. Now, what we recognized in the last slide was this second equation. It's just the first equation multiplied, in the last lesson, it's the second equation. It's the first equation multiplied by 2. So I number my equations. I solve the top one for x. So first equation I solve for x, and then in the second equation there's x, and I substitute. So I do the algebra out for this, and if any of this goes too fast, you can stop the video and do the algebra out yourself to convince yourself. But I multiply negative 1 times 2 and negative y times 2, and I get negative 2 minus 2y, and then I have plus 2y here. So these together, negative 2y plus 2y, come out to 0. There's no y's left. So this time I get two numbers equal to each other, which is always true, so you get an infinite number of solutions. I have one line, and there are an infinite number of points on the line. So there are infinite points I could choose that would make both equations true. All right, let's see. We have some for you to try. So solve these by substitution. And they are all have a variable that's either already isolated or easily isolated. So try these 4 problems and come back and see the answers. And here you go. Here are your answers. Hopefully you tried it. And if you did not get these, please get some help, see the tutoring lab, email me, make an appointment, get some help from a classmate. Do not go on just not knowing. And also check, maybe I need to go over a problem again. You never know. The answer is, could be a mistake on my part, especially if a couple of you email me. I'll really look at, I need to look at it. So thank you for joining me in this lesson of math, in this edition of Math Teacher to Go, and I will see you next time.